Hi, I'm Rich Brunner, and I would like to talk about the new Intel i960 JX microprocessor. We've recently announced this. It's our new low-end embedded processor. The 960 architecture has been around for quite some time, going all the way back to the mid-1980s with the announcement of our earliest 960KX microprocessor. And now we've announced the JX, which is a new processor to fill in the role that had been filled by the KX. I'm with Intel's Embedded Processor Division in Chandler, Arizona. Okay, there are a number of things I'm going to talk about concerning the 960JX. First, we'll talk about the feature set. And I'd like you to bear in mind as I talk about the feature set that this processor is intended for embedded systems that, say, cost only a couple $100 at most. Typically, the system might be a lot less than that. And bear in mind that these systems tend not to be CPU-centric, but instead the embedded processor is merely an incidental part of the system. And so the price of the processor has to be in line with that system design cost. And some of the constraints we get from that market are such that we need to be providing more than 30 VAX-MIPS of performance for less than $30. We'll talk about a number of special features that help our processor in price-constrained systems. Typically, embedded systems of this class will implement very slow instruction memory. Maybe it will only be 16 bits in bandwidth. It will be very slow memory typically. Maybe it will be 120 nanosecond burst ROM, and the instruction memory will not be shadowed. Our challenge as designers in this case is to provide acceptable 32-bit performance and still overcome these inherent limitations in fetching of instructions. We have a number of power-saving features that help us to operate at half a watt at 3.3 volts at 33 megahertz, and a number of other things that we'll talk about that help us to maintain a small footprint as well as to reduce overall system power. And lastly, we'll talk about performance results. One of the goals for our processor was to have 2.5 times better performance than the current low-end 960 embedded processor, the i960KA. And I think we've met that goal very well. One last thing I should mention for performance result is that we had the requirement of doing much better than 1 microsecond interrupt response time. Okay. The 960 microprocessor, the JX that I'm going to be talking about, is a single-cycle RISC engine. It is a 3-ported register file. Therefore, it's possible to execute one instruction while returning the results of the other. We have a number of concurrent units in addition to the integer core. We have a multiply-divide unit that performs a 32 by 32 multiply in 4 cycles, and that executes in parallel with the integer core once the multiply is issued. We also have the ability to execute load and store operations in parallel with the integer core once the load or store is issued. And our data cache is non-blocking. In some senses, we would consider ourselves to be a hybrid RISC because we provide a number of complex addressing modes and other functions that traditionally would be performed in RISC processors with a number of instructions. One of the challenges for us, because we typically go into a system with a very slow bus, is how do we increase the effective instruction bandwidth? And by providing complex instructions, somewhat complex instructions with slightly more complex addressing modes, we can accomplish that goal. And we'll talk a little bit more about what those complex addressing modes are. We have a 4 kilobyte instruction cache and a 2 kilobyte data cache. The instruction cache is two-way set associative, and the data cache is direct mapped. One of the interesting things about embedded processors is that the instruction cache is typically larger than the data cache. And again, this is because of the problem I've mentioned of typically slower instruction memory. Also, for an embedded processor, typically the application is well known, and generally that kernel is what the embedded processor will be executing for most of its lifetime. And typically you can fit that kernel into an instruction cache if it's big enough. So that's why we made the trade-off for a bigger instruction cache than a data cache. We offer the processor in ranges from 16 to 50 plus megahertz, and we implement the Intel clock doubler mode for this part. Our dry stone performance ranges from 28 to 41 VAX MIPS. It ranges with the megahertz, the frequency of the part. The current implementation is 750,000 transistors, and it's 64 millimeters square as far as die size goes. At the moment, we implement this in 0.8 micron process, 3-layer metal. The reason we chose this process is because it provided us the optimal cost performance price point that we needed for a low-end embedded processor. Future versions of the 960 will of course explore smaller process geometries and higher frequencies. We offer 3.3 volt and 5 volt versions, and we're in a 132 pin grid array and plastic quad flat pack. The good news is we're already taped out, and availability will be in late '94. Here's a block diagram of the JX microprocessor. You can see that we have a number of integrated peripherals on this part. This adds value to our customers, and it helps to reduce the amount of glue logic and additional ASICs in an embedded design. You'll notice our bus controller unit up in the right-hand upper corner. This bus controller contains a bus queue that has 3 slots, and each slot has up to 4 words of data in it. This allows the bus controller to be somewhat decoupled from the execution of the integer core. Another thing that the bus controller implements is programmable bus width. This is on a per-region basis, and it allows the processor to support a number of different memory width parts. We also have transparent endianism support for both big and little endianism, and again that can be programmed on a per-region basis. The 960JX has a homogeneous endianism model. That means that typically it will only support big or little in a particular application, but a number of other processors, 960 processors, can support a heterogeneous endianism where you can program big or little endianism by region. We also offer unaligned address support, and we'll talk a little bit about that later. Another one of the integrated peripherals on the 960JX that is a standard part of 960 processors is our integrated interrupt controller, which has 32 interrupt priority levels and also provides a non-maskable interrupt. We have a traditional interrupt architecture in that we have an interrupt table that is used to determine the address of an interrupt handler once an interrupt is delivered. Our integrated interrupt controller provides fast sampling and debounce modes and has a number of other interesting options that help to optimize interrupt performance. We have 2 integrated timers in this part. These are 32-bit timers. And one of the useful features of the timers is that they can also be used to generate an interrupt that will wake the processor up from a halt mode that we'll talk a little bit more about later. The only other thing I'd like to point out on this slide at the moment is the 8-set local register cache and the 128-bit interface between that local register cache and the 3-ported register file. This will allow us to do heavyweight call and return operations in very few cycles. Okay, we offer, as I said before, a number of complex addressing modes in hardware. The reason that we do this is to increase our effective instruction bandwidth. And we made the analysis that the little bit of extra silicon area necessary to implement these complex addressing modes was worth the gain that we received in code density and performance. Most of these addressing modes, 6 of the 9 addressing modes that are in the 960 architecture, are directly executed by the i960 processor hardware. And just to talk a little bit about the terminology, in the table, OFF12, which stands for 12-bit offset, and DSP32, which stands for 32-bit displacement, are 2 of the most basic modes that the 960JX processor supports. A number of the complex addressing modes that derive from that then allow a register or a scaled register to be added to that. And I would say probably one of the most complex addressing modes that we offer in the 960 architecture is the instruction pointer relative addressing mode at the bottom of this page. In its full-blown form, that can take a 32-bit displacement and add that to the instruction pointer adjusted to point to the next instruction. This is useful for generating position-independent code, and our compiler has a way of optimizing the generation of position-independent code to use this mode only when necessary. Let's talk a moment about our programming model. The 960 architecture has 16 global registers and n sets of 16 local registers. Each context has its own private set of local registers. When an interrupt or a call occurs, the current set of local registers are pushed to a local register cache, and then a new set is allocated for the interrupt handler or for the target of the call. Now, because we have that 128-bit interface from the register file to the local register cache, we can perform that operation in typically 6 cycles. I'm going to move to the next slide to discuss this feature a little bit more. In the picture, you can see that, again, when an interrupt or a call occurs, the current local register set is spilled to the top, pardon me, not spilled, but put into the top of the local register cache. Now, as your call depth increases, eventually the local register cache will become full, and we will need to spill in some way to take the oldest set in the local register cache and spill that or move that to external memory. When that happens, the processor does that automatically. Of course, there is a small performance penalty that you pay when you do spill from the stack. Because of that, we provide the mechanism to reserve some number of these frames in the local register cache for the usage of high-priority interrupts. The reason that we do this is so that when an interrupt is being delivered, you are guaranteed that the current local register set can be placed in the top of the stack, and you will not get a spill from the bottom of the stack. So we always reserve some number of free frames for high-priority interrupts using this mechanism I've just described. This is one of the things that we do to guarantee that we will have significantly less than 1 microsecond interrupt response time. Another thing that we've recently added to the 960 architecture is predicated execution, or conditional ops. Because this happens to be a scalar processor with no branch lookahead, taking a branch can be a painful activity. It will take 2 cycles to execute a branch, one to issue it, and the second cycle to branch to the target. If we can avoid branches, then we can improve our performance. Also, for certain sequences of code, conditional ops offer us a way to increase our code density. This example here shows one of our conditional operations. The C fragment actually, as you can see, does a comparison of A and B. And if A and B are true, then X will be set to Y plus Y1. And if it's false, X will be set to Z minus Z1. We can use our conditional operations to execute this code very efficiently and avoid branches. You can see in the assembler fragment of 960 macro code that first a comparison of A and B are done, and that sets the condition codes. Followed by that is a conditional add. If the condition codes indicate that A and B are equal, the add will take place. Followed is a subtract. If A and B are not equal, then the subtract will occur. As I said, this helps us to avoid branches and to increase our code density. We have numerous other operations like this, but this serves to illustrate the power of the conditional operations for us. Another feature we added to the architecture are subword comparisons, byte and 2-byte comparisons. This allows the compiler to work on character and short-int data without first generating a mask for a 32-bit register. Lastly, we have a byte swap instruction. In addition to the transparent endianism support inside the bus controller unit, we also allow software the capability to explicitly byte swap data using this instruction. We have a number of special features that relate to memory accesses. First of all, we have a 1 kilobyte on-chip data RAM. What we can do with this on-chip data RAM is allocate the interrupt vectors and some number of key constants and variables to it. Because, as I said before, we have an interrupt table, it's to our benefit if we can cache some of the entries of this interrupt table on this internal data RAM. Certainly our latency to this data RAM is much less than going to external memory for the entry. In addition, our profiling compiler can analyze a program and make the decision to relocate certain heavily accessed constants and variables to this RAM. We have built-in unaligned memory reference support. Many of our customers value this capability and are unable to quickly or oftentimes just cannot change their application to avoid unaligned data. So they can take advantage of this mechanism, which provides transparent support of unaligned accesses. There is some performance degradation in performing these unaligned accesses, but it is transparent to the program. I've already mentioned that our bus controller allows us to transparently support both big and little endian memory accesses, and how some members of the i960 family support a heterogeneous endianism model, where you can program different regions of memory to have a different endianism. Lastly, to improve our code density and to support bursting on the bus, we provide 16-byte load and store operations which go back and forth between 4 of the registers. We've done a number of things on this part to decrease the amount of power that is used and to make the part more suitable for low-end embedded processors where power is constrained. First of all, our typical power usage at this point is a half watt at 3.3 volts at 33 megahertz. We made some decisions about whether the part should be superscalar or scalar. And when we looked at the price performance and the processes available to us, we made the decision to go with an enhanced scalar processor. One of the benefits of an enhanced scalar processor is that it is less power than a superscalar. That's not to say we don't know how to design superscalar processors. The 960CX, which was announced in 1988, was one of the first commercially available superscalar processors. And certainly there will be more superscalar processors from Intel and from the Intel 960 division. But enhanced scalar was the right choice for the Intel 960JX. We do a number of microarchitectural features that help to reduce power consumption also. One of them is the processor predicts when a memory operation will occur, and then it powers up the D-cache. Another mechanism is that we don't actually drive the microcode ROM when we're not executing microcode. In addition, there are certain debug features that we disable also when they're not being used. Another mechanism we use is we throttle the clocks of an idle unit. That means we stop the clocks of an idle unit instead of allowing it to continue to execute and generate garbage, which we then must ignore. A feature we provide that helps to reduce the overall pin count and footprint of the part, as well as to reduce the system usage of power, is a multiplexed address and data bus. Lastly, we provide an explicit power management mode through our new halt instruction, and we estimate that it will reduce approximately 90% of power consumption on the part. As I mentioned earlier, any external interrupt or a timer interrupt can wake you up from the halt mode. Okay, it's generally acknowledged at this point that there is no good benchmark for measuring the performance of an embedded processor. Part of the problem is, say for example you wish to run SpecInt. You need some portion of the Unix file I/O up and running on your part in order to be able to run the SpecInt benchmark. I would suggest that you be highly skeptical of vendors who claim SpecInt performance on their part and question them whether they have actually done the porting of the Unix file I/O or how they have measured that part of the performance equation. For want of a better benchmark, we're going to use dry stones. And the first thing you can see from this graph is that dry stones probably doesn't tell you very much. The problem, the dry stone benchmark fits entirely in the data cache, such that even the half cache part has approximately the performance of the full cache part. And because it fits into the cache, the bus performance also is not as much of an issue. But it is one benchmark that helps us to determine whether our integer core performance is acceptable or not. One of the better benchmarks would be to look at imaging performance, and that's shown in the bottom graph. This happens to be taken from the Adobe PostScript page Gopher. And it shows for various memory profiles that we have met our goal of doing much better than 2.5 times the performance of the i960 KA, which is the unit 1 here, down at the very left hand of the page. Typically in the embedded space, our customers have their own applications that help them to determine the overall performance. And Intel can help in measuring the performance of those benchmarks on our processor. Okay, now we're here to the processor summary. We offer a number of proliferations of this part, starting from a low-power, lower-cost solution that has a half cache, it runs at 3.3 volts, and scaling all the way up to a high-performance part that uses the clock doubler mode and has a 5-volt operation. This table here probably shows all the relevant parameters for the different proliferations. And you can see that a number of megahertz range are available. You see our typical power for the very low power solution is half watt at 33 megahertz. And let's see, what else would be useful to note about this? Probably the only other thing that I can add to this foil is to say that we are investigating higher frequency operation proliferations, as well as looking into tighter process geometries and looking at ways of increasing the cache size as well. So the 960JX is a new core for us, and we expect to be increasing its capabilities very rapidly in the years to come.